Assalamualaikum dan salam sejahtera. My name is Awang Muhammad Izhar bin Awang Ahir, and our group will present to you series connected DC motor. So first and foremost, as you can see from the image, the series connected, this is series connected equivalent circuit, which is the field winding F in series with the armature winding A. The field windings are made of bigger size of diameter wire, and the field resistance are much smaller than shunt machines of comparable size. This is to avoid dropping too much of the source voltage across the field winding. Next, we have relevant equations, which is voltage equation of series DC motor V or VD is equals to EA plus IA times RA plus RSE, which EA is armature induced voltage, IA is armature current, RA is armature resistance, and RSE, or you can call it RF, is series field resistance.
Hi, my name is Muhammad Haziq bin Saidun and I am presenting the torque speed characteristic and DC motor speed control of series DC motor. Torque speed characteristics. To approximate the relationship between magnetic flux and field current, we employ a linear equation, which is V equals to Kf times IF, where Kf is a constant that depends on the number of field windings, the magnetic circuit's geometry, and the iron's pH properties. The relationship between V and IF is nonlinear due to magnetic saturation of the iron. Next, IA equals to IF in series machines, thus we have V equals to Kf times IA. Substitute for V in the EA equals to Kv omega m and T developed equals to Kv IA, resulting to EA equals to Kk F omega m IA and T developed equals to Kk F I squared A. When feature voltage are applied to the equivalent circuit, which result to Vt equals to Rf times Ia plus Ra times Ia plus Ea, which then can be rearranged to get armature currents and torque developed, which is stated in the equations below. Next, when this slide shows T developed equal to 0, despite the speed must be infinite, the motor speed is limited at high speeds due to rotational losses, bursts on the windage, and eddy currents. The no-load speed can reach the dangerous levels. When the load disconnects, it is critical to have protection devices that cut off electrical power to a series machine. At the very low speeds, the current IF equals to IA becomes large, then magnetic separations occurs. Therefore, the starting torque is not as large as predicted. Next one is speed control of DC motor. There are three methods to control the speed of DC motor. The first one is vary the voltage supplied to the armature currents while holding the field constant. Second one is vary the field current while holding the armature supply voltage constant. The last one is insert the resistance in series with the armature circuit. The first one of speed control of DC motor is variation of the supply voltage. Permanent magnet motors and separately excited motors can both be used with this approach, because the field current and flux vary with terminal voltage. Varying the supply voltage is not a suitable method of speed control for the shunt motor. There is little change in speed when both the armature supply voltage and the field current are increased because they tend to cancel each other out. In normal operation, the drop across the armature resistance is small compared to EA, and we have EA equivalent to terminal voltage. Since we also have EA equals to Kv omega m, we also can write omega m equivalent to terminal voltage over Kv. As a result, the speed of a permanent magnet motor or separately excited motor with constant speed currently is roughly proportional to the source voltage. A DC motor that is connected in series can also be controlled by varying the supply voltage. However, in this instance, the flux does not remain constant. Second one, speed controlled by varying the field current. By altering the field current, the speed of the motor that is either connected to a shunt or excited separately can be controlled. The means to regulate the field current are provided by the rheostats, adjustable resistor. The last one is speed control by inserting resistance in series with the armature. This method can be used with any kind of DC motor, shunt, series, individually excited, or permanent magnet. The torque-speed relationship for a shunt-connected motor is torque developed equals to Kv over Ra times Bt minus Kv omega m. Speed can be adjusted by varying a rheostat that is in series with the armature, which the operation can be seen in the figure below. The circuit diagram shows the circuit with the adjustable rheostat, and the V torque speed characteristic shows the result based on the graph from the circuit. And the last but not least, for series connected DC motor, torque developed equals to KKF V squared T divided by Ra plus Rf plus KKF omega m squared. It is important to note that the torque at any given speed decreases if Ra is increased by adding resistance in series with the armature. That's all from me. Thank you.
Assalamualaikum and hi, my name is Akil and I will be presenting about the application of the series DC motor. So basically, series DC motor are suitable for any application that requires strong starting torque. Okay, DC series motors are only utilized in application where speed variation is possible. Application that requires constant speed cannot be performed using series motors. It is commonly used in cranes, drilling machines, vacuum, or anything that requires traction and high static torque. Next is the pros and cons of series DC motor. So the pros of series DC motor is it has a very simple circuit and design, a very high starting torque, and it is very cost effective as it is very simple and easy to maintain. The downside of series DC motor are the speed control regulations are very poor, and it should always require being loaded before starting the motor or it could be damaged. And lastly, it is not suited for the application where load on the motor is completely removed. And that's all from me. Thank you for watching.